everyone, thanks for joining. In this project, we keep SGP4's speed and correct its biases in real time using a lightweight ML residual model. That gives us meter-level short-term accuracy, fewer false alerts, and fewer unnecessary maneuvers, so operators save fuel and extend spacecraft life. It works for both satellites and debris, and drops in as a low-risk, scalable add-on to existing workflows. So why now, and what's the cost of the status quo? Quick baseline. TLEs are the standard public orbital elements with epoch and a drag term. SGP4 is the global workhorse propagator, blazing fast microseconds per step, perfect for screening tens of thousands of objects. The trade-off is simplified physics. In LEO, errors drift 2 kilometers within days, mainly from drag and unmodeled effects. In short, today's pipeline favors speed over accuracy, which is great for coverage but costly for decisions. And that trade-off creates a very real operational problem. We are at 50,000 plus tracked objects and roughly 1,000 alerts a day to triage. SGP4's LEO drift loads alert lists and drives a high force alarm rate. False alerts lead to unnecessary avoidance maneuver, burning fuel, shortening mission life, and ironically, increasing debris risk. Operators spend time and propellant on events that don't need action, and our aim is to cut that noise without slowing operations. We focus on the 24 to 72-hour window where screening and planning happens. By improving accuracy there, we filter out borderline false alarms, save propellant, extend mission life, and reduce debris risk, advancing space sustainability. And this is a drop-in add-on, not a workflow overhaul. Even trimming 20 to 30% of borderline alerts can save large constellations on the order of 50 to 150 maneuvers per year. And what does success look like in concrete terms? 3 clear targets. Number 1, accuracy. At least 50% error reduction at 24 hours and 70% at 48 hours across LEO, including debris. Secondly, performance, so millisecond level inference per object, so we scale to 50,000 to 100,000 plus items. And last but not least, safety. We have built-in guardrails with automatic fallback to SGP4, so we can never do worse than baseline. Now, here's how we achieve that, our hybrid concept.
Hi, I'm Sumit, and today I will bring you through the technical side of things. So for this concept of hybrid SGP4 and machine learning residuals, we fuse SGP4 with the machine learning residual model. So the core is simple. We basically predict and subtract the error SGP4 missed using the formula over there. The machine learning basically acts as a perturbation function. So if SGP4 is accurate, the correction is 0. So this gives us near numerical accuracy at SGP4 speed. So this requires a dual two-step architecture as given. So we have the offline, basically the training style things, where we generate a high fidelity truth track, computing the residual error given by the formula earlier. We then train the model on this error time series. Then we also have the online, obviously the operations side of things, where we run the SGP4 and the machine learning model simultaneously. The correction here is instantaneous. Our safety mechanism is basically the fail-safe. So if the predicted correction is deemed as an anomaly, we will flag it and revert it back to the raw SGP4 output. So what specific models and orbital features power this high-speed correction? We basically use compact neural networks. We use FFN, basically means feed-forward network, which handles a non-sequential regression, removing the circular drift or the steady track bias. We also plan to use the LSTM, long short-term memory, which captures periodic terms and temporal dependencies. So the inputs for this includes delta T's since epoch, B asterisks, and crucial orbital phase embeddings to learn periodic errors. We prioritize simplicity for robustness. So here are the results which validated our approach. The details are also in the report. We baseline SGP4 error at 6, 12, and 24. We didn't do 48 yet. And our setup used a small FFN model, 2 times 64 neurons. We basically used Optim.Adam, as you can see over here. We then tested project models, generalized models, and specialized debris-focused models. We used root mean square error to evaluate the definitive percentage improvement over the baseline. So the performance leap from our results was dramatic. The results validated our strategy. So as you can see, the ISS, a specific model cut the 24-hour TLE error by more than 18 kilometers to just 102 meters of minimal 99.43 error reduction. As for debris, Cosmos 2251, the generalized model actually failed, which degraded accuracy by minus 1.35%. But if we used a debris-specific model, it actually achieved a significant 56 to 59% error reduction. So you can see, debris, due to its high dynamical variability, absolutely needs its own tailored model. So this is just the same results but visual format. The raw blue line grows quasi-linearly to multi-kilometer levels, driven by drag bias, while our hybrid error, orange line, stays virtually near 0, achieving meter-level accuracy for satellites. By removing this systematic bias, the remaining error is small, random, and predictable. We then transform the issue from a propagation problem to a minor noise problem. So what does this meter-level accuracy mean operationally for collision avoidance? So improved accuracy polarizes risk estimates, basically making true threats clearer. We have false alert reduction. We basically project a 30 to 50% reduction in false alerts. This saves almost 300 to 1,000 fewer analyses per day. Debris impact is also lower. Our more than 50% gain for debris directly reduces false alerts across the 70 to 80% of the catalog, which is actually just debris. Last but not least, we also impact maneuver avoidance, basically eliminating 20 to 30% of borderline alerts, which saves large constellations almost 50 to 150 maneuvers annually, which conserves both fuel and extends mission life. So to ensure this operational gain is safe, we also build strict guardrails, which Ava will bring you through.
Our system is safer by design. It never performs worse than baseline. We continuously check residual magnitude and consistency. If a correction looks out of family like a kilometer scale jump, we flag it, trigger human review, and fall back to raw SGP4. Because we model residuals, analysts can clearly separate SGP4's physics output from the ML correction for explainability. And next step on the roadmap is to add covariance/uncertainty via ensembles or a particle filter, so corrected states flow cleanly into PC. Now, How does this plug into what you already run? This is a drop-in add-on, no edits to the SGP4 COM. We achieve meter-level accuracy with negligible inference overhead compared to SGP4. It's milliseconds per object and embarrassingly parallel. So scaling to 50K to 100K plus RSOs for catalog-wide refreshes is straightforward. The reference build is Python/PyTorch, and we export via ONNX to slot into C++ or other SSA systems. And before deployment, we have to handle the ethics and policy side. We reduce risk through transparency and gradual adoption. The system is assistive, not prescriptive. Humans stay in the loop to avoid automation bias. We log all inputs and outputs, keep the model transparent, and advocate independent VNP before operational use. To address fairness, especially for debris, we use debris-specific models and start in shadow mode alongside current tools. And these choices reflect deliberate trade-offs. We balance accuracy, speed, and maintainability. We chose GP speed with learned physics over SP everywhere because SP isn't real-time at catalog scale. And for accuracy, we use per object models on critical assets. For example, roughly 99% gains on ISS and regime clustering for the rest. A fully generalized model even degraded ISS by roughly 7.39%, and for debris, generalized models slipped 0.7% to 1.3%, so we use debris-specific models. Version 1 stays self-contained on TLE features, space-weather inputs are optional later. This is lean and open source, so total budget is roughly $7,000 SGD, mostly a GPU workstation plus some cloud credits. Label is in coin. Stack is Python or PyTorch. Ongoing cost per satellite is tiny, fractions of a cent, so preventing even a handful of unnecessary maneuvers quickly repays the initial $7,000. This is our roadmap. So in phase 1, we plan to have POC on ISS with FF and Skyfield, so target is over 80% improvement. In phase 2, we plan to broaden regimes, add debris-specific models, and LSTM for periodic errors, confirm 50 to 60% reductions on Cosmos 2251 and Feng in 1C. In phase 3, we hope to have operational readiness, so uncertainty quantification, large-scale conjunction schemes, ONNX packaging for SSA integration. And in phase 4, we plan to have PC integration pilot, Iridium 33 validation, and a shadow mode partner track.
On to the conclusion, we basically have hybrid residual learning is an immediate and essential upgrade for SSA or space situational awareness, delivering both operational efficiency and long-term sustainability. So on the technical feasibility and innovation side of things, we have redefined accuracy by achieving 99.43% error reduction for the ISS, transforming kilometer-level HGP4 to meter-level accuracy of just 102 meters. We also have debris innovation. Our hybrid approach is the first in literature to demonstrate measurable consistent improvements for debris objects by reducing positional errors for Cosmos 2 fragments by 56 to 59%. Last but not least, our solution is also interpretable and fast. The solution is grounded in theory, augmenting physics-based SGP4 with learned systematic corrections, making it fast and interpretable. On the space sustainability impacts of things, we basically cut operational waste by reducing false alerts by 30 to 50%. We also prevent unnecessary precautionary maneuvers, which conserves fuel, extends mission lives, and reduces debris generation. Our solution is also ready to deploy because our hybrid model is implementable, testable, and provides meter-level accuracy with negligible operational cost. So with that, our model is a prerequisite for responsible stewardship, and we are confident that this approach will provide immediate tangible benefits to satellite operators worldwide. We welcome any feedback you may have for us. Thank you very much for watching our presentation.